The purpose of this video is to help you learn to use the JET aircraft design and analysis software by demonstrating how to use the software to optimize an aircraft for a particular design mission. The aircraft we're going to optimize is an F-106, a 50s vintage which flew through the 80s, Century Series Interceptor and air-to-air fighter. And we've modeled this, as you can see on the left, modeled the geometry of the aircraft and also the weights of the aircraft here in the center. This is for the aircraft with no external fuel tanks, but we do have the internally carried weapons that are carried inside the weapons bay. We have a really good geometry model of the aircraft, and as a consequence we have a really good aerodynamic model of the aircraft. These values for CDOs and Ks and the CLmax, etc., are very accurate to the actual aircraft characteristics. So we've got a good model of the aircraft to start from. We also have the J75 engine model down here, and its characteristics are correctly modeled by the software. Over here on the right we have the standard F-106 constraints, constraint diagram, and down below we have the design mission that we're going to optimize for. Note here that this mission is a 250 nautical mile radius air defense mission. The aircraft starts out and goes 200 miles at 40,000 feet and 0.9 Mach, then dashes in full afterburner for 50 nautical miles still at 40,000 feet and Mach 2 now. And then when it gets there, it pops up to 45,000 feet and stays there for 3 minutes in full afterburner, delivering its weapons, and then returns to base at 0.9 Mach and 40,000 feet. Ends with a 20-minute loiter at 10,000 feet, and then the aircraft lands. So that's the design mission we're optimizing for. And if we note here, we have a positive solution to the sizing equation, so we can go ahead and jump right into the optimizer. Let's just take note of the wing geometry that we're going to depart from: aspect ratio 2.2, taper ratio 0.01, 60 degrees of sweep, 1% camber, and 4% thick. And so those need to be in our range of values. We're only going to optimize for aspect ratio and sweep, so we want to set the other values to the correct values for this wing. Otherwise we're optimizing some other wing. So we have the 0.01 taper ratio, the 4% thickness to chord, and 1% camber shown here, and those won't be iterated on because they're the same values in both cells. And then we want to bracket the values for aspect ratio and wing sweep for the F-106. It's 2.2, so we'll go from 1.8 to 3 aspect ratio. The sweep is 60, so we'll go from 44 to 64 in sweep. So everything's ready to go. Notice over here this drawing of the airplane. Because right now for this demo I'm running the software in Office XP, you'll actually see the wing plan form change as the different iterations occur. In later versions of Microsoft Office that won't happen. You won't see any change there, but it's kind of fun to watch in this demo. So here we go. We hit the calculate button and watch the iterations occur. We're trying different sweeps and different aspect ratios, looking for the optimum. Alright, we've got a good run. We've got a good carpet plot. Down here at the bottom's got to be the best wing. Here it says 2.8 is the one we picked up on. There's several right there together. So let's go down and look at 2.8 and see if that's the true optimum. Okay, 2.8, I see 2756, but I see 2603 here for the aspect ratio 2.6 and 50, so that's probably the absolute minimum. It's also the minimum sized aircraft gross weight, so that's the one we'll use for our optimum wing. Now in theory, because this is a solution to the sizing equation, if we size the whole aircraft down with this shape wing, it would be the optimum and it would only weigh 10,000 pounds. But of course we can't do that because we can't size the fuselage down. The fuselage has to carry the weapons and the pilot and the fuel and everything. And so when we size the aircraft down, we can't actually achieve this 10,000 pound takeoff gross weight. But this is still the optimum wing shape, and we can apply that and see how much we can actually size down the aircraft. Alright, so aspect ratio 2.6 and sweep angle of 50. That's not a terrible looking wing, but look, we're using more gas than we're carrying. This wing got heavier. It's true. However, if you look on the constraint diagram, the wing's too big. It's a lot too big. It should be clear over here at 63 pounds per square foot wing loading, and we're at 50. So let's drop this down. It should be the same ratio, 63 to 50, so let's go to 550 from 698 and see what we have. Alright, now there we're getting somewhere. We can drop the weight of the aircraft 1,000 pounds. Let's go 34,300. No, I'm sorry, 34,300. And we can go even smaller, 34,100. And we've got 50 pounds extra. We'll stop there. So 34,100. Now we've got some issues. The aircraft's unstable. That's because when we unswept the wing some and moved the wing forward, the aircraft, the wing itself is forward because it got smaller in area. So that's easy. We just move it back. Let's go to 26 or so. And that's not bad. 5% static margin. When it goes supersonic, it'll have 30% static margin, something like that. So that's a reasonable balance for this era. We'd go unstable with a more modern airplane, but we're talking about an airplane designed in the 50s. So let's just optimize it there. Alright, what else do we have here? We've made the aircraft better. We've saved a lot of weight. We've saved some cost. We could go back to the other and see just how much cost we saved, but probably $4 or $5 million per airplane. And about the only other thing we might notice is that CN beta is kind of high. So if CN beta is 0.0028 and we only need 0.002, maybe we'll try 95 or so for the vertical tail area. Alright, 0.0, let's try 93. Alright, 0.0021, that's close enough, plus or minus 10%. Okay, and we've got another 300 pounds, so 33,800. Just a little bit short, 33,837. Okay, so there's just a little bit of margin there. So there's our aircraft. Now it looks like the wing's still too big on the constraint diagram, so we can go a little smaller. Let's try 530. And there's about as far as we can get, but we dropped another 150 pounds, so 33700. And that's where we're going to stay. We got a 50-pound margin on the fuel, and the aircraft's far away from any of the constraints, and it meets all its requirements, and we've saved probably $5 or $6 million if we went back and checked on the original aircraft design. So that's a 10% savings just by optimizing the wing.